All right, so let's talk about our final report that you did for today. Then we'll talk about the homework assignment for today. Then we'll finish up our Connect 4. Then we'll talk about the final homework assignment, and then the course will be done. So, just as a reminder for any of you who are taking the next class, the 537 class that immediately follows this one, we basically pick up right where we left off here. So if you need to take that class anyway, I might recommend that you take it right away when the things are still fresh in your mind. That class starts next Monday at 6 p.m. until 10 p.m. I know some people, technically it's during the spring break week for Concordia. A couple people emailed me asking if you are going out of town, I am going to still record the lecture. So if you're going to miss the first week, not the end of the world. So just an FYI for that. But if you're not registered for that now, definitely get registered if you are entertaining that. Okay. So the report for today was write a 3 to 5 page paper discussing the role of object-oriented programming in modern programming solutions. How does object-oriented programming compare to procedural programming? Is procedural programming dead? Discuss the history of object-oriented programming. What was the first object-oriented programming language and what was the motivation to create it? How did object-oriented programming languages evolve? What do you predict will be the next evolution in computer programming? So hopefully this was a somewhat interesting paper. How does object-oriented programming compare to procedural programming? So let's start off with that one. What did you, let's just say you had a test and somebody asked you to compare those two. What might you say? Or what did you say in your paper? How do those two compare? Don't all speak at once. Just the exact same thing? The same languages? Okay, step by step. What's object-oriented? We've been using a lot of objects in our last two programming assignments. How was that different than the previous programming assignments where everything was done procedurally? Let's think about last week as an example. Your last two homework assignments before, not the one that's due today, but the previous two, were very similar assignments, correct? One of them was written using two-element arrays to represent fractions. The other one was represented using fraction objects to represent fractions. Wouldn't you agree that the two-element array version, the procedural version of our add fractions homework, was much messier in terms of you just glanced at the code, glanced at main, than the one that had objects? When we encapsulated things in objects, when we created a fraction object, all the details of that object were hidden inside of the fraction class, right? Sure, it's still there. We had to write it, but after we wrote it and it worked, to use a fraction, all we had to do was create a couple of instances of fractions, add them together, and we're off and running, right? So all the details were hidden. So procedural programming, while it is much more step-by-step, it's linear, monolithic in nature, if you will, you also see a lot more details because not only are all the public interfaces, the moving parts that the programmer is going to be working with while they're solving problems, not only are those exposed, but also all of the details that aren't something that a programmer will directly interact with on a common basis. They're also exposed. It's like walking into a house without drywall. You'll see all the wires and things like that behind the walls. An object-oriented language allows us to hide all those details. The example I think I probably gave in class was the telephone thing sitting over here, where we had the procedural version of a telephone was you see all the wires exposed and all that stuff, but it is a telephone. It still works. We see the public interface. We can go and push the buttons. We have the handset, all that stuff. But then we also saw all the wires that a human being is never going to have to touch in order to use the telephone. The object-oriented version of the telephone had all those wires and things that the human being isn't going to have to touch inside of the case, inside the object. And only the public interfaces, only the buttons and the handset were exposed. Okay? So that's the difference between object-oriented programming and procedural programming. Let's see. So, having said that, is procedural programming dead? Maybe another way of asking that, is it fair to say that object-oriented programming is better? You think it is better? So if it's better, does that mean that procedural programming is dead? Okay. So there is a difference between a procedural programming language and procedural programming. We spent half of this course using an object-oriented language, but writing procedural programs. Does that make sense? So procedural programming is not dead. Procedural languages, maybe a different story. Are they dead? Give me an example of a procedural language. Definitely procedural language. Although, did you know there is an object-oriented version of COBOL? It does exist. But the 089 version of COBOL, which I think was the last time it was updated, maybe there's a 92. There might be a 1992 update to COBOL. But clearly, we're dealing in an old language. COBOL is definitely procedural. A more common procedural language for us might be like C. Okay, it's kind of the great-great-grandparent of all the things that we use today. C is at the core of modern programming. So that kind of segues into the next step here in this paper. Is a language like C dead? The follow-up question to that is, what does it mean for a language to be dead? Is anybody still writing C programs today? Or, let's follow it up, is anybody still writing COBOL programs? Surely nobody's writing COBOL today, are they? I mean, what a waste of time. So do you think anybody in the world is still writing COBOL? Who? When? Why would somebody still be writing COBOL? Why would somebody still be writing C? Give me some examples of situations where people would still be using these old procedural languages.
Didn't you say for your wife's situation, it's easier to hire people who are still specializing in it, revamp the entire system?
Yep, absolutely. So my wife is a COBOL programmer today. Now, she's maintaining programs that are 30 years old, but she's also writing new programs that are 2 days old because their entire system is based on COBOL, and it's been around forever and ever and ever, so to speak. At least a half a second. That's an inside joke, but she wasn't listening.
I was. You said half a second. You were making fun of me because it's my expression that I use. He's making fun of me.
I wasn't making. It was an inside joke.
I was trying to listen.
That was making fun of it.
COBOL is all old and stuff, 30 years old, and they're maintaining it. But then other people are writing new programs that are 2 days old.
Right, but then I said the half a second thing, which was funny.
Yeah, I was listening, but it wasn't funny. It was not.
She's
funny.
laughing.
It's so not funny. That is not funny. You're making fun of me.
I'm not.
You are too. You're mocking me.
I might be.
I am very affronted right now.
Very affronted. All right. So in any case, procedural languages do still exist. You will likely not find new things being written from scratch unless you're being forced into adding to old things. Make sense? So you will likely not find a new company come about today that decides, you know what, we're really going to bring COBOL back into mainstream. Similarly, if let's say there's a new video game company that comes out today, they're probably not going to say, let's go write some C programs. They're probably going to be using actually C++, which in its own right is an old object-oriented language. But why are they using that? because a lot of the libraries for writing the graphic user interfaces and the OpenGL and the DirectX 3D animations and all that crap are all written using old C++ libraries. Some are written using old C libraries. So these older languages, even the procedural ones, they're not dead because there's enough stuff written in them from the early days of computing taking over the world that those languages are still around. Now, there's no way for us to know whether they'll always still be around, right? But as far as I can tell, Western Illinois University, where my wife works, there's no discussion about stopping, them switching to something other than COBOL. There's not enough money. They'd rather spend $1 million a year maintaining what's old than spending $30 million today to update everything that's ever been written. It's the trade-off. So in the long run, they'll spend more money, but at least it's a slow bleed, relatively speaking. Okay? So it's not fair to say that procedural programming is dead from any perspective. We spent half this course writing procedural programs just because that was the right tool for the job. Objects don't always make sense. Sometimes you're just writing a quick little method that does something. Don't need an object for that. Similarly, procedural languages are still used for older maintenance of programs. Okay? Now, discuss the history of object-oriented programming. What was the first object-oriented programming language, and what was the motivation to create it? What did you find to be the first object-oriented language?
Simula.
Okay. And what was the motivation to create it?
Ship simulations.
Okay. Why did it need to be object-oriented?
They were combining different attributes from different ships into different classes of objects.
Okay. Did that have to be object-oriented?
This was used in analog programming.
What was the problem with previous languages? Where did procedural languages start showing their weaknesses?
Data. It manipulates data.
Okay. So data abstraction
Yeah.
was a problem because you see all the details. Okay. Now,
Reusability.
go ahead.
Reusability.
Okay, reusability would definitely be a big thing, right? Writing things that are packaged that you can then easily take to somebody else. Think of it like, let's just come up with a far-fetched example. Let's say that you have 500 marbles, all right? And I'm giving you the marbles or something like that, okay? Is it easier for me to hand all these marbles to you in one big, handful? Or is it easier for me to put them in a bag first and then hand you the bag? Putting in the bag first, right? So we're encapsulating the details, encapsulating the marbles into a single bag, and I'm handing you the bag. So now that's an object that contains the stuff that you want, rather than here's all the stuff that you want. Okay? So how did object-oriented languages evolve? So you mentioned the first one, where did it go from there? Did they immediately take off? Were they cool day one? Did they almost fall apart? What do we find? Took off right away? What were some other object-oriented languages that you...
Smalltalk.
Okay, Smalltalk. What can you tell me about Smalltalk?
They were inspired by the ideas that was used in Simula.
Okay, and who did Smalltalk then inspire? You may or may not have run into this in your research. Smalltalk used a specific type of structure that modern day programming languages object-oriented languages don't necessarily use, except for one. Objective-C. Let me do it here. So Smalltalk use something called message passing. So you would have sender. Actually, you would have it receiver and message, like that. So for instance, if we have a string in Java, string s, then we say s.length. The equivalent message passing version of that would be s length. Send the message length to the variable s. Okay? So the language that uses this today is a language called Objective-C. So Objective-C has a message passing type syntax that it sort of modeled after Smalltalk. Where our other modern languages, C, C++, C#, Java, use dot notation. S dot length, so on and so forth. All right. Let's see. So last one, maybe, hopefully there's some fun answers here. What do you predict to be the next evolution in computer programming? Is object-oriented programming the end? Is there something else? What's the...
GPU.
Okay, tell me about it.
So a lot of GPU will be used in software.
Okay, so that's more of a tool using the graphics processing unit.
Yeah.
Well, let's go down that path real quick. So why do you think you're going to see that used in software? It's actually already happening. There's a technology I have in mind that's using it called OpenCL. Why do you think GPUs are going to become a important thing to computer software? See, right now when we write our programs, most of our high-level programs are compiled, right? What's compiling mean? Compiling translates from a high-level language to a low-level language, right? And low-level languages have a one-to-one relationship with the CPU. So the CPU has a whole big list of magic tricks that it knows how to do, and every line of code in a low-level language translates into exactly one of those instructions, one of those little magic tricks. Now, when you think about our CPUs in our computers today, you might have a dual core or quad core, and there's some 6-core ones, then you have some dual quad cores or dual 6-core, but that's kind of the end of it. You have, let's just call it a high-end single processor computer today has a quad core processor in it. So it could do 4 things simultaneously, okay? If that made sense. How many people does it take to change a light bulb type thing, but for problems that where more than one thing can happen at once, it could potentially do up to 4 things at once. When you think about our graphics cards, a lot of our graphics cards today, their processors are called GPUs, graphic processing units. And the graphic processing units, many of these cards have 256 or 512 cores. So our Intel processor, Intel Core i7 quad core, has 4 cores versus 512 cores in a GPU. Why aren't they putting 512 cores in my Intel processor? What's the difference between a core in a GPU versus a core in a generic Intel processor? When we think about our Intel, the CPU that I have, this has an i7 in it, I think. So this is a quad core i7. This is a general purpose CPU, correct? It maybe knows how to do 500 different things. There's 500 magic tricks that it knows how to do. Just making up a number, but let's just say it's something like that. The cores that are on the graphics card might know like 5 magic tricks. They're all about floating point math. So graphics cards know how to do math. They know how to do it fast. And they can do 512 math problems at the exact same time. So it's limited on what it can do. But it can do a lot of those limited things very, very, very quickly. And when you think about displaying pretty pictures and colors and polygons and things like that on a computer screen, all that is fast math. Okay, things are being manipulated and added and subtracted and multiplied and divided over and over and over and over and over again every fraction of a second. All those cores are working very, very hard. Now, our graphics cards are in our computer 100% of the time, correct? Always sit inside of our computer. Right now, I have my graphics card inside my computer. It's displaying this crap on the board. Now, certainly this is a highly, highly intensive video game that we're playing right now, right? What percent of my graphics card's capability do you think we're utilizing right now? Pretty small percent. My graphics card can probably handle a little bit more than displaying a static white screen, correct? So is it fair to say that our GPU, the graphics processor in this, is sitting idle most of the time right now, right? So we say with CPUs, our general purpose processors, those things sit idle 95, 98% of the time. It's not doing crap. In fact, there's plenty of applications out there, like one of them, SETI at Home, another one's called Folding, which is a physics research company, where you install it in your computer, and when your computer's not busy doing anything else, you lend your CPU cycles to solving some sort of world problem. You know, either searching for aliens or solving, you know, mysteries of physics and that kind of crap. Because it's taking advantage of a truth that is, our CPU, when our computer is on, is usually not busy. When it is busy, we don't want it doing anything else. We want it making us happy, right? But most of the time, it's not busy. Well, that's even more true with your graphics card. Because when you're using your computer, when you're surfing the internet, when you're downloading a file, things like that, you could conceivably keep your CPU busy somewhat, right? Wouldn't you say that unless you're playing a video game, that your graphics card is pretty bored most of the time? Do you need a $700 graphics card to correctly show a web browser? Or will the $5 graphics card that came in a computer 12 years ago show a web browser just as well? It's a web browser. It's got 4 colors, tops. Sometimes you go, oh, here we got, maybe we have like 6 colors. So, okay. Very simple screen though, right? So really, the GPU is a huge untapped resource. Now, when you're in the middle of playing a video game, so, you know, whether you're, whatever game it is, you're playing a video game, your processor is going to be pretty busy, your graphics card is going to be pretty busy. That's not an opportunity for your computer to be doing a whole lot of extra work for somebody else. Okay? For most of our modern day video games. What are all our games when a new game comes out today? It's just trying to push the envelope for what our modern day computers are capable of doing. Why? So you go and buy another computer tomorrow. Because you can't play the game you wanted, even though you just got the computer a week ago. So in any case, it makes perfect sense to start trying to take advantage of the GPU. Would you agree that a lot of the problems we might solve on our CPU, our general purpose processor, are math problems? Several of them are not math problems. There's tons of stuff that don't involve math. But don't you think there's a lot of math that the processor knows how to do? So we're general purpose people, right? You can give us a math problem. You could tell us to do dishes. We could drive to the grocery store. We could do all sorts of different things. One of those many things we know how to do is math. A graphics card can't go grocery shopping. Can't do all this general purpose stuff. It can do math. So wouldn't it make a lot of sense to take all the math that we might throw to our processor and instead throw it to the GPU and let the GPU do the math? Because it's not busy doing anything else. That's all it's good for. That makes sense? They don't have heart surgeons giving eye exams. Because you don't want the eye doctor doing heart surgery. Those two people have their specialties, right? Okay, so there's a technology called OpenCL that is for that exact purpose. What it does is then you have to build it into your software, but it allows your software to leverage the GPU in your computer. Now, that's more of an operating system level technology, but having said that, there isn't a great reason why you could not build into programming languages. It would really be at the compiler level probably. Then maybe step 2 might be at the runtime level, but to take advantage of all the resources your computer has. That's kind of maybe the big punchline there is our computer is a box with a bunch of resources in it. And we really, up to now, don't use those resources that wisely. Now, because human beings are easily satisfied some of the time, our computers are so fast that we don't care that all these resources are being wasted, as long as things seem fast enough for us. But if our computer starts feeling sluggish, now we care if things are being wasted. It's already slow, and you're wasting the extra stuff. Kind of make sense? You know, if you had a race car and you just use it to drive around Mequon, which is a funny thing because the guy who owns the country club over here has a race car that he just drives around Mequon in. And I mean, it's like one of those cars that you just idle it, it's past the speed limit or something. But, you know, in any case, that car, 99% of the time, isn't going anywhere near its full capability, right? It's a whole lot of wasted resource, but you can still use it. But now, what happens if you have a car with a broken engine? Or a car that's engine is almost broken, so it can go 2 miles an hour. Now, all of a sudden, you care that the thing isn't really performing up to snuff. Does that make sense? So, one goal we might have in general is let's not waste any of our resources. We'd rather have the power and not need it than need it and not have it. Right? Okay, so certainly taking advantage of the GPU might be a direction we go there. Anybody come up with anything else for next evolution of programming languages? Or did everybody just say GPU? This was supposed to be the interesting part of the question. So besides him, raise your hand if you said GPU. Okay, so then we have 3 people who said something other than GPU. What did we say? What's another thing that how programming languages could evolve? What's with the silence? We do a quiz on it. What did you write about? What did you say about the evolution of the programming languages?
I missed this part. Just I learned about the history and what is the programming language, object-oriented programming,
Mm-hmm.
and some of the benefits for this language.
So we're looking at this last part. What do you predict to be the next evolution of computer programming?
Yeah, I missed this part.
Oh, you skipped that part? Okay, what about you?
I didn't say much on it.
Just made crap up?
No.
This was supposed to be the fun part of the paper. What did you say?
I don't know what it's going to do, but it's going to do something, thinking along the lines of artificial intelligence,
Mm-hmm.
that if you're trying to mimic human intelligence and thought patterns, you're going to have to go some step further than procedural, and definitely some step further than just classes and methods.
Mhm.
Because we do so much more, but I don't know what it's going to be.
So maybe even some level of self-programming. Like, you know, you get the language pointed in the direction of a solution to a problem, and then it evolves from there. Something like that. So evolutionary programming, where the language through artificial intelligence solves problems that you didn't originally intend for it to solve. That could certainly be, I mean, it's sci-fi, but that's certainly potentially possible, right? You know, there's an interesting sci-fi series called, well, the original book was called Ender's Game by author Orson Scott Card. And in one of the later books, there is this computer mind, if you will. So we'll call it a computer program. It was based on something called the Mind Game from the very first book. And it was essentially a piece of software that was intelligent, more intelligent than anybody who was programming it. And it would self-program. It would change the way it did things on its own without any human interaction. So is that possible? Is it sci-fi? Who knows? But you know, I could see certainly something dealing with artificial intelligence starting to play into future day programming languages. It only makes sense. Even if you get to the point, you know, maybe an interesting question might be, and this is relevant to something that's been in the news the last several days. Bill Gates, old Microsoft guy, had a quote, it might have been yesterday, that within the next 10 years, I think maybe he said 10 to 20 years, but I thought it was just 10 years, that 50% of the jobs that human beings are doing today will be replaced by robots. Isn't that interesting? So, does that mean that robots will be writing our programming, our programs? Be software writing programs? So somebody had to program the robot. Could the robot then sit down and write programs? Therefore, could the robot rewrite themselves? It becomes an interesting, interesting type thing. So I think artificial intelligence is certainly an interesting take on that. Okay, so questions about the paper. All right, so now let's go and let's look at the homework assignment. Something to do with cards, right? Is this one easy? Yeah. Create a class called deck that represents a deck of 52 cards. The deck should be able to shuffle itself, display itself, and deal a card. Dealing a card should return the card from the top of the deck. Dealing a card twice in a row should not return the same card. That is to say that dealing a card changes the position of the top of the deck. Okay? Got it. So let's go in here. I'm going to go ahead and open up Driver. Well, actually, we don't want to mess up our game we were working on. So let me just create a new file, new project. Killing me. All right. Let's call this cards. We'll create our new class. We'll call this guy driver. And we'll put our main method in here. Perfect. Just testing to make sure everything's hooked up right. There. Perfectly spelled hello world. All right. So we have that. Now we are to create a class called deck. New class, deck. Now a deck is supposed to represent a collection of 52 cards. Okay, well, in order to represent 52 cards, we need to have a card object. So I'm going to go in here, I'm going to create another object, another class. We'll call this guy a card. Did I say anything about cards in here, like what they should be? Okay, so it's freeform. So a card, we're going to say a card has a display value and a card has a suit. So it could be ace of clubs, something like that. Okay? The constructor for our card is going to take in a display value, and it's going to take in a suit. And we'll set this dot display value equal to display value. This dot suit is equal to suit. All right. And then we're going to go ahead and create a public method called display that knows how to display a card. So if this is the ace of clubs, we probably want it to display the display value, followed by a space, followed by the word of, followed by a space, followed by the suit. Ace of clubs. Make sense? So we'll say system.out.println, this dot display value concatenated with a space of space concatenated with this dot suit. All right, so that's our entire card object, at least as of right now. So to kind of test this real quick, let's create a couple of cards out here. So we'll create a card C1 is equal to a new card. And when we create a card, we have to pass it two pieces of information, the display value and the suit. So we're going to call this guy the ace of clubs. And we'll create another card, card C2 is equal to new card 8 hearts. Something like that. We'll say C1.display, C2.display. So we're just testing out our little card objects here. We built a couple of cards. The first one represents the ace of clubs. Second one represents the 8 of hearts. We'll display those two, and it should give us a nice pretty ace of clubs, 8 of hearts. Displayed to the screen. Okay, so that's our card object. Now, with the next class, the 537 class, that class we talk a lot about something called a data structure. We've already been introduced to some structures. Arrays are a structure. Last time we talked about multidimensional arrays. But objects in and of themselves are data structures. That is a structure built for holding data. This is a data structure capable of holding two pieces of information, and then it also has a method for doing stuff with that information. All right. So now I have a data structure specifically built for holding information related to cards. Now, what are we supposed to do inside of DEC? DEC is supposed to create a collection of 52 cards. So the value, the data that a DEC controls, because a DEC is also going to be a data structure, it's an object, it's going to control an array of card objects. Okay, so I'm going to create a private variable in here. Now, why am I making this private? Why am I making, well, here, let me actually create it, then you're going to tell me what it's all about. Why is this guy private, and what's this entire thing called? So we have a variable called the cards. What kind of animal is the cards in terms of an object? Objects are filled up with 3 different kinds of members: methods, constructors, and fields. Which of those 3 is this guy? It's a field. Fields are variables, right? We know it's not a constructor or a method because it doesn't have open and closing parentheses on it. So fields are the variables owned by our classes. Why did I make it private? What does it mean to have a field be private? I can only get to this field if I'm inside the DEC class. Right.
Can you go back to card for a second? Just take this. I missed one part. Okay, got it.
All right, so a DEC is a collection of cards. Now we're going to create the constructor for our DEC. Public DEC. And this guy is going to set, well, we'll say this dot the cards is equal to a new card array 52. What this does is it creates, inside the variable name the cards, a card array. That is 52 spots in contiguous memory where each spot is capable of holding a card object. Keyword being capable of holding. There are no cards in this array yet. It's capable of holding 52 cards. Okay? So if I were to print out system.out.println this dot the cards, it's going to give me crazy memory address. Similarly, if I say system.out.println this dot the cards at bucket 0, it's going to print out null. There is not an object there. Okay? So as of right now, my deck object, the constructor, just instantiates my, initializes my array to be capable of holding 52 cards, and then I print out a couple of pieces of information. I print out the value of the cards, which should be the memory address, which points to the beginning of that array. And then the second thing I point out is I try to print out the card that lives at bucket 0 of my array. But at this point, I've never put a card in there. Correct? So the guy that lives there should be nothing, should be null. So I'm going to go into driver. We'll just real quickly create an instance of deck called D. And this guy should call the constructor. We know that's a constructor because it's following the new keyword, right? Anytime we follow the new keyword, is always a constructor. So inside deck, we'll instantiate our array and print two things out. First thing it's going to print is a memory address. Second thing it's going to print is null. Oh, I said print, not println up here. The null was there. It just was all on one line. There you go. So here's the memory address of my array. And there's the value that lives at bucket 0 of my array, which is nothing, null. Null is the keyword, which means the empty memory address. Okay? Why is it empty? Well, because it's a container built for holding a card, but I have not actually put a card there. Okay, so part of my job then for the constructor for deck is to actually fill that array up with my 52 playing cards. Right? Now, cards come in a bunch of flavors. They come in 4 different suits: clubs, diamonds, hearts, spades. Right? 4 different suits. They also come in a bunch of different display values. 2, 3, 4, 5, 6, 7, 8, 9. Jack, queen, king, ace. Okay? So what I'm going to do here is I'm going to create a couple of arrays. I'm going to create a string array called the suits. And this guy is going to be equal to diamonds, hearts, clubs, spades. So it's an array with 4 elements in it, and the 4 elements are the 4 different suits. Similarly, I'm going to create an array. Actually, I would say I would create an array, but I don't even need an array for this one. In fact, a string probably be easier to work with. So I'm going to create a string called the display vals. And this guy is going to be the string 2, 3, 4, 5, 6, 7, 8, 9, Jack, Queen, King, Ace.
Why'd you put ace last?
Oh. What? Because this is a generic game, so ace doesn't necessarily have a value of 1. Ace is, actually, I would say ace always comes last. Why shouldn't I put ace last? Out of curiosity. All right, so here's all my suits. I have 4 different suits. And here are my different display values. So I want to make a 2 of diamonds, a 2 of hearts, a 2 of clubs, a 2 of spades. I want to make a 3 of diamonds, a 3 of hearts, a 3 of clubs, a 3 of spades. So for each character that's inside of this display val string, I want to make a new card with each of these suits. Oh, that's a good question. That's why I don't have this in, that's why I didn't put it in a, that's why you probably did it in an array. I'm actually just going to treat it as a special case, since I already wrote this much. So, here I'll do, I'm going to put an extra little space there. Actually, I'll do this. I'll put a T at the end of that. That'll be better. So at the end of my little string, I'm going to put a T. I'm not going to do it in the middle at the end. I'm going to do it right there. After the 9 comes the T for 10, then Jack, Queen, King, Ace. I can't put the 10 in here because that would be 2 characters in the string. So I'm going to say T here. Alternatively, I could have built an array with these guys in it. And then I could have stored the 10 as its own string. But I'm already down this path, so I'm just going to go this way. So for int I is equal to 0, I is less than the display vals dot length I plus plus. So for each character in here, I want to do something. What am I going to do? Well, I want to create a new card. I want to create a card for the diamonds, for the hearts, for the clubs, for the spades of the character I'm currently looking at here. So that means I need another loop for int j is equal to 0. J is less than the suits dot length j plus plus. So I'll go through all the suits. So for each element of my string, for each number, each display value, I want to create a card for each of my suits. And what am I going to do? I'm going to say this dot the cards at bucket what? Now I'm going to need some way of indexing my array. So I'm going to say int pos is equal to 0. Because the very first card I'm going to put in my array will be at bucket 0. Then I'll make pos become 1 bigger. Next one will go at bucket 1. Then bucket 2, then bucket 3, then bucket 4, so on and so forth. So the cards at bucket pos is going to equal a new card. And that card is going to be built with 2 pieces of information. The first piece of information is display value. Second piece of information is suit. Okay? And my display value must be a string, according to my constructor for card. So when I say the display vals dot char at I, I'll be getting a char. How do we turn a char into a string? Concatenate it onto the empty string. So I'm going to say new card, empty string, concatenated with this dot the display. Oh, it's not this dot, just the display values. The display vals dot char at I. So that'll give me my string version of my character, either 2, 3, 4, 5, 6, 7, 8, 9, T, Jack, or JQKA. And then I want my suit, which will be the suits at bucket J. Okay? So the cards at bucket pos quick curiosity, I'm not bleeding anywhere, am I? Because I just found blood on my arm. Let me know if you see something funny happening. Chances are I just put my arm in something. It's nothing. I'm not cut or anything. But Just don't let it go on too long without it might even be dried food for all I know. Okay. What was I talking about? Oh, okay. So at bucket pause, we're going to put a brand new card. That card is going to be the empty string concatenated with the character at bucket I in the display vals, as well as the suit that lived at bucket J. Then I need to remember to increment pause. So the first card goes at bucket 0, next one goes at bucket 1, next one goes at bucket 2, so on and so forth. Just found more. All right, well, just let me know if something bad starts happening. That's not food. That's kind of messed up, actually. Okay, so we'll increment pause. Now, keep in mind, well, as of right now, this will work. We have one little problem. That problem is that sometimes we're going to be coming in here to card, and the display value will be the string t rather than the integer, or rather than the string 10. That makes sense? But I really want it to hold a 10. So what I'll say here, inside of the constructor for card, I'm encapsulating this question, I'm hiding this question inside of the card object. I'm going to say if this dot display value dot equals t, then say this dot display value equals 10. I'll treat t as the special case. And you could have gotten around this by creating your entire, instead of using a string for your display values, you could have used an array where you could have stored the 10 as a string. But that's not what I did. I stored a t, so this is why I have to do this. Okay. So back here in deck, spin through. Fill up each bucket with the new card. Increment pause each time. That should be all we need to do for creating a deck. So now I'll go ahead and I'm going to do a public void display so we can display the contents of a deck. So what I'm going to do is I'm going to go through here and I'm going to display each card in the deck. For int I is equal to 0. I is less than this dot the cards dot length I plus plus, and I'll say this dot the cards at bucket I, which is a card, dot display. So I'll tell that card to display itself. Okay, so we'll come back out to our driver. After we create our deck, we'll say d.display, and we should see our 52 cards. 2 of Diamond Hearts Club Spades, 3 of Diamond Hearts Club Spades, all the way up to Ace of Diamond Hearts Club Spades. And you'll notice that the T's got translated into 10s because of the if statement we put inside the constructor for card. All right. Now, so we have a deck of cards. The deck of cards seems to be filled up with all the right crap. Now we need to have the ability to shuffle a deck of cards. We also need to have the ability to deal a card from the top of the deck. So we need to do a couple of different things here. For deck, besides keeping track of the cards, we must also keep track of an integer, maybe called, let me call it cur top. So when we create a brand new deck, we're going to set cur top equal to 0. Okay? cur top is equal to 0, because that's the current top of the deck. What does it mean to deal a card? Public card deal says, give me the card at position cur top, then make cur top be one bigger than it used to be, so that the new top of the deck is one bigger than the last top of the deck. So I'm going to say card temp is equal to this dot the cards at bucket cur top. Then I'll say cur top plus plus. Then I'll say return temp. So I'll go ahead and temporarily hold on to the card that lives at bucket cur top. Then I'll increment cur top. Then I'll return the card. I need to do it this way. Well, if I'm going to do it in more than one line, I need to do it this way because if I just return this value, I will not have the ability to increment cur top. Unless I take advantage, this would be an example of a place where you could take advantage of your knowledge of the plus plus minus minus operators. This is the foolproof way of pulling this off, what I've written here. It doesn't require that you've remembered how plus plus and minus minus work. Okay? So what am I doing? I'm saying temp is equal to whatever card's at cur top, and whether I say plus plus cur top plus plus, or cur top equals cur top plus 1, it does not matter because all this happens all in one line. The alternative here would be to say return this dot the cards at bucket cur top plus plus. This one line accomplishes the exact same thing as these 3 lines. But you should only use this one line solution if you are 100% positive you remember how the plus plus operator works. That if plus plus comes after cur top, we get the current value of cur top now, and then it becomes 1 greater than it used to be. If the plus plus comes before, it becomes 1 greater now, and we get that new value. Okay? So, you're not cooler if you write it in this one-line version. It's correct to write it this way, but it does rely on you knowing the difference between cur top plus plus and plus plus cur top. Make sense? So, if you never want to have to worry about that, just do it in 3 lines, and nobody's going to like you any less. I temporarily stored it, changed the value I needed to change, then I returned the value I temporarily stored. Does that make sense, the example I'm giving there? When we teach about plus plus and minus minus, we're always looking for good examples of times when you might take advantage of something like that. And this would be one of those examples. But I promise you, this is not a time complexity issue like we've dealt with the last couple of classes. So whether you do this in 1 line or 3 lines, I doubt very much you're going to notice any speed difference in your program. Okay, so that's what the deal method does. Deal method gives us a card from the deck, from the array of cards, that's at the position cur top. And then we make cur top be 1 more. So if I go out into driver, and maybe I say for int I is equal to 0, I is less than 5, I plus plus, and I say d dot deal dot display, I should display 5 different cards. I'm working my way through the deck. Does that make sense? So it's going to deal me the first card, then the second card, then the third card, then the fourth card. So I should see 5 different cards be displayed to the screen. But because my deck was not shuffled, there just happened to be a bunch of 2s and 1 of the 3s. All right, questions about that? All right. So now, the last part that we need to be able to do is our deck needs to be able to shuffle itself. So I'm going to write a method here. Well, I'll make it public for now. We can decide whether it should be public or not, but we'll say public void shuffle. And what's shuffle going to do? It's going to jumble up my deck of cards. So what I'm going to do is I'm going to create my random number generator. Random r equals new random. And I want to randomly generate two numbers between 0 and 51. That is I want to generate a random number that references a legal bucket in the cards. So I'm going to need a variable called, well, I can call it whatever I want, but I'm going to need a temporary variable because I'm going to be doing a swap. I'm going to generate two numbers somewhere in the array, and then I'm going to swap the cards at those positions. I'm going to do that like 1,000 times. Go ahead.
So just going back to your dealing the cards, so when you walk through those 3 steps, what it does is your cur top is like the card of bucket 0, and then your temporary card, which is the one that you're dealing, is the card at cur top, and then cur top moves to the second bucket.
Becomes 1. Yeah, the second bucket.
Okay, because to bucket 1, because what I did for my dealing cards, well, let me go back to it. For my, hold on, where did I put this? Okay, there it is. Sorry. What I did for dealing cards was like, you print the deck at it prints the deck at bucket 0,
Mm-hmm.
and then it takes and then it moves all of the cards left a bucket.
Oh, shifts them all up 1.
Yeah, and then there's nothing at the end, so it's actually getting rid of cards from
The card's actually gone.
Yeah, is that okay?
Yeah, and that's reasonable. The problem, there's nothing wrong with that. A issue you have with that, so if we compare this to real life, is when you run out of cards and you need to build yourself another deck.
Oh.
So imagine it like this. If we had a real deck of cards in real life, what you're doing is after we deal that card, the card only exists once, which is true. That's how real life works, right? So when I deal a card off the top of the deck, that card lives here now, not any longer in the deck. So you're accurately representing real life, correct?
Oh.
But there's no way for me to get that card back into my deck. So if I'm going to play a second game or something like that, I'll have to generate a brand new deck because essentially all my cards burn up at the end of the game. So it's not like there's a right or wrong. It's just kind of a factoid.
I'm just burning up all my cards.
Well, it's just a fact about the way you're solving the problem. So you'll have to remember that when you go to game number 2, you'll have to build another deck. No big deal, right? Deck D equals new deck. Back in town. Yeah, all our cards are filled back up. So no harm, no foul. For my implementation, the card actually only exists once, but there's 2 different ways of getting to it. One way is it still lives inside my array, inside my deck. The other way is I have a pointer out here that I handed to the player or something like that. But they both are the same card. But when I go to start again, my second game, all I have to do is move cur top back to the top and then reshuffle the deck. So one's not necessarily better than the other. It's more of the just the nature of the problem we're solving, I guess. Okay, so for shuffle, I'm going to generate 2 random numbers. So it's going to want me to import java.util here. I'm going to need a temporary variable. I'm going to call it temp because if I have 2 buckets, 2 positions in my array, I can't just overwrite this guy because when I do that, I've lost this guy. I can't put him here. So I need to take one of the guys, store him here. Then I can overwrite here. Then I can overwrite here. Does that make sense? So I'm going to need that temporary guy to do the swap. So let's say we're going to do for int I is equal to 0, I is less than 1,000, I plus plus. We'll do 1,000 swaps. That should jumble up our array pretty good. If you don't like that, you can do 3,000 swaps if that makes you happier. So I'm going to need to create 2 different positions. So I'm going to need 2 integers, int pos1, int pos2. So I need pos1 to be some number between 0 and the length of the cards minus 1. And it just so happens that the next int method that takes an integer gives us a number between 0 and whatever number you gave it, non-inclusive. So I can say pos1 is equal to r dot next int this dot the cards dot length. So we know that this number will be the number 52, right? So this will generate a number between 0 and 51. That's what that line of code does. So I'll get pos1 will be some number between 0 and 51. Oh. Pos2 will be some number between 0 and 51. Then I'll say temp is equal to this dot the cards at bucket pos1. Then I'll say this dot the cards at bucket pos1 is equal to this dot the cards at bucket pos2. So I'll overwrite pos1 with whatever's at pos2 after I've preserved the card that used to live at pos1 inside temp. Then I'll say this dot the cards at pos2 is equal to temp. That'll do my swap. Make sense? So now back out here at driver, we'll create our deck d.display. We've already seen this show us all of our cards in order. But then but before I display, I'm going to say d.shuffle. Then I'll say d.display. We still have all our cards, but now they should be all jumbled up. That makes sense? If you don't think 1,000 is enough times, then do it 10,000 times. Really jumble them up. Okay, so I think that fulfills, oh, the other thing we should probably do here is inside of deck, when we shuffle, we should go ahead and set this dot cur top back to 0. So in between hands, we'll shuffle, and then the top of the deck becomes the new top of the original top of the deck after we shuffle. So when we first create a deck, we have our nice in-order deck, just like if you just bought one from the store. Then we can shuffle it up, and every single time we shuffle, cur top gets set back to the beginning of the deck. That way we can start feeding stuff off there, so we can play our first hand of poker, for example. Then after that, we collect all the cards, shuffle it. Now the top of the deck's back at the top of the deck. Start dealing again for the second hand. Does that make sense? Now, an interesting thing here, I'm somewhat curious. What if I was, it's likely so astronomical that we wouldn't be able to, it wouldn't be done. So it's kind of going back to our time complexity problems. What are the chances of you shuffling a deck of cards and having the result be all the cards in order?
Over 2 factorial.
So extremely unlikely.
Yeah.
Seems like, right? But that would be an interesting program to write to see if what percent of the deck is in the original order. Kind of see what I'm getting at? That will give us an idea of just how good our shuffle is. Let's actually, let's write that. That allows us to explore a couple of interesting things here. In order to tell whether or not my deck is in order, I need to compare the original version of my cards to my final version of my cards, correct? Now, to do that, what I need to do is I need to create a second card array, my original card array. So I'm going to create a private card array, the original cards. Okay. And when we fill this up, we can say this dot the original cards at bucket pos is equal to that. Then we can say this dot the cards at bucket pos is equal to this dot the original cards at bucket pos. Now, there's a problem with doing this. When I go and I'm going to have my original deck of cards. So kind of like I have two, if we're doing this in real life, I have two decks of cards sitting in front of me. Okay? I buy them off the shelf at Walmart or whatever. So they're both in this exact same order to begin with, right? I'm going to leave this guy over here in the correct order. I'm not going to shuffle him. But I'm going to come over here to this guy, and I'm going to shuffle him. Does that make sense? And then I'm going to say, is this guy the same as this guy? As I currently have it written, and let me actually, let me show it to you this way. Inside my display, I'm actually displaying my individual cards. I'm going to write a second method, public void show both arrays. And rather than displaying the cards, I'm going to display the memory address that the cards point to. So I'm going to say for int I is equal to 0, I is less than this dot the cards dot length. We can say this dot the cards or this dot the original cards. They both have the same length. I plus plus. Then we'll say system.out.println. This dot the cards at bucket I concatenated with, let's just do a space, a dash, a space, concatenated with this dot the original cards at bucket I. Okay? So I'm going to do show both arrays. Come back out here to driver. D dot show both arrays is going to show that both of those arrays are filled up with identical memory addresses. Ooh, hello. Give me a moment. Oh, sorry. I never actually gave a value. This is actually an interesting thing. The original cards, I just started filling it up. I never gave it a value. I never set it equal to a new card array 52. So this dot the original cards is equal to a new card array 52. So I have two separate arrays, two separate decks here. Each of these decks is going to get filled up with cards. But what card am I putting in there? I'm putting in the same card. So bucket 0 of this array and bucket 0 of this array point to the exact same one card up in memory. And you'll see that when I display both arrays, notice that all these memory addresses are identical. This is bucket 0 of one of the arrays. This is bucket 0 of the other array. Notice it's the exact same memory address because that card only exists once. That makes sense? Okay. Now, by doing that, I can determine whether or not the exact same card is in the exact same position later on. And what I mean by that is, let's go into driver. Before I show both arrays, I'm going to say d dot shuffle. Now, because we did not change the way shuffle was written, shuffle should currently shuffle only the cards. Shuffle does not touch the original cards. Does that make sense? So, if we, let me diagram this a little bit because this is kind of an interesting thing we're doing here. So here I have the original cards. And then we also have the cards. Okay. Now, just for the sake of this example, let's assume that the original cards and the cards are 3 bucket arrays rather than 52 bucket arrays. All right. So this might be how it looks. Maybe this is bucket 0, 1, 2 for that array. And this is 0, 1, 2 for this array. Notice that my 3 cards, these are cards, guys with the C's in them. My 3 cards only exist one time. 3 unique memory addresses. This card lives here, this card lives here, this card lives here. So maybe these are memory addresses maybe that's 100. Well, actually, let's just do it like, let's say that's memory address 14. '59 and 91. That's where these 3 cards actually live. One of them lives at memory address 14. One of them lives at memory address 59. One of them lives at memory address 91. So inside of my arrays, this card does not live in this bucket of the array. A pointer to that card lives there. That means the value at this bucket of the array would be 14. Just like the value in this bucket of the array would be 14. This holds the memory address which points to the card that lives at memory address 14. Just like this guy holds the memory address, which points to the card that lives at memory address 14. This guy would be 59. This guy would be 91. 59. 91. Cards exist once. I have 3 cards, but I have 2 arrays, and each of those arrays hold all 3 cards. But notice that bucket 0 of the first array has the same memory address in it as bucket 0 of the second array. Bucket 1 of the first array, same memory address as bucket 1 of the second array. And we see that in action right here. Oh, sorry, I've already shuffled. Pretend like you didn't just see that. Bucket 0 of the 2 different arrays have the exact same address in them. So that card only exists once. They just both point to that one card. Does that make sense? Now, if I shuffle the cards, so right now my shuffle method only shuffles. I didn't rewrite shuffle to deal with the 2 different arrays. My shuffle method only deals with the cards, not the original cards. All right? So if I come in here and I shuffle these guys around, that is, maybe I make I have to kind of keep these just to keep my own sanity. Let me just do that one little shuffle. It's very weak shuffling. So now I've shuffled the cards. So this guy is in the same order it originally was in. This guy's no longer in the same order, right? Now bucket 0 of the cards points here, which is the same place as bucket 1 of the original cards points to. Does that make sense? So now if I print out these 2 memory addresses, if I print out the original cards at bucket 0, I'll get a 14. But if I print out the cards at bucket 0, I'll get a 59. So after I shuffle the cards, I will not necessarily have the same memory addresses in the same order. But the cards still only exist once. Does that make sense? I have not changed the nature of my cards up here. These cards still only exist one time. All I've done is I've jumbled up the order of the pointers inside of the cards, but left the original cards alone. So these pointers are in a different order, but this guy still points to the card at bucket 59. This guy points to the card at bucket 14. This guy points to the card at bucket 91. Just like this guy points to 14, 59, 91. So if I come in here to driver and I go ahead and shuffle, I'm only shuffling the cards, which is what I just did, which means that my 2 different arrays will not necessarily hold the same memory addresses, right? So we'll see that now they hold different memory addresses, because one shuffled, one's not. That make sense? This is actually going to be a good learning experience for comparing objects. Now, what we want to do is we want to shuffle the deck of cards, and we want to print out a percent of the number of cards that are in the same position as they used to be in. That make sense? So we're going to look at the shuffle deck, and we're going to say, what percent of these cards are positioned in the exact same place as their equivalent card was originally? So I'm going to look at bucket 0 of these 2 arrays. Are these guys pointing to the same card? They're not. Bucket 1, these guys pointing to the same card? No. Bucket 2, are these guys? Yes. So 1 out of 3, 33%. We're in the same position. Does that make sense? Okay. So we're going to go and calculate that. So we're going to write another method inside of deck. And keep in mind that we're writing things in deck now that don't belong in card games. These are just tool type things for teaching things, okay? So we're going to write public void, let's see, let's do public, int's good enough. We don't need to know that it was 33.33333 repeating percent. We'll just truncate it. Good enough. Gives us enough for darts and hand grenades, right? Public int get percent same. And what we're going to do is we're going to loop through all of our arrays. Now, last time, did we talk about parallel arrays? This is the first time you're hearing me use that phrase? Okay, good. That was my intention. Then I++. So let me quickly talk about parallel arrays. We've already been talking about for the last 10 minutes. Parallel arrays is when we have two arrays with the same number of buckets in them. And each bucket relates to the equivalent bucket in the other array in some way. So for instance, we might have, let's say we needed to hold a first name and a last name. So we have one array of first names, another array of last names. Bucket 0 of the first array is the first name that relates to bucket 0 of the second array, which is the last name. So parallel arrays, bucket 0 of both of them means something. Okay. In this case, I have two different arrays that are the same exact size. And they all hold cards. I know, so the parallel array problem solving here is I know that these two arrays are identical at a particular bucket when the pointers in that bucket are equivalent. So if, for instance, bucket 2 here, since the pointer to the card is 91 and the pointer to the card is 91 here, that means we found a match. Those two guys have a matching card and we want to add 1 to some sort of count. So we're going to go through all of the cards inside the cards, which has the exact same length as the original cards. That's one of the qualifying natures of parallel array problem solving, is that the arrays need to have the same number of elements in them. And we're going to have an integer here, int matches. We'll start off at 0. We'll say if this dot the cards at bucket I is equivalent to this dot the original cards at bucket I. If that's true, we'll say matches plus plus. Okay? Then at the end, we're going to return the integer version, that'll force it to truncate, of matches. Actually, hold on, we want it as a percentage. This will make life easier. I'm going to turn that into a double for right now. We know it's only going to be 1. It'll be 0.0, 1.0, 2.0, 3.0, but we're going to have to divide it by the number of elements, which is going to give us a decimal number. Okay? So we can either typecast it to a double or just have it be a double to begin with, so the math doesn't just turn to 0. Because if I took the number, let's say I took the integer 5, and I divided it by 10. 5 divided by 10 is what? 0.5, right? But if you're doing integer math, 5 divided by 10 is 0. Because integers can't hold the decimal places. It's 0 remainder 1. Well, in this case, 5 goes into 10. Well, that would be 2 times. 10 goes into 5, 0 remainder 5. So we're not getting the decimal places. So I'm going to make this a double. That way we're capable of holding the 0.5. And then we'll multiply that 0.5 by 100 to get us our percentage. All right, so in the end, we're going to return the integer version of matches divided by this dot the cards dot length, the number of elements inside of the array. So if I found 5 matches out of 52, 5 divided by 52 will give me some percentile. Okay, and that'll give me the integer version of that. Now, if I want to get the actual value though, let's multiply this, the actual percentage as a percentage, let's multiply by 100. So if it was 5 divided by 52, this would be 5 divided by 52, which is that, times 100, which is 9.6%, but in this case we're returning it as an int, so it'll return 9%. Okay? Does that make sense? How truncation and stuff like that works? It won't round, we'll just cut off the 0.6. So that's what get percent same will do. So we're going to go ahead, we're going to go out to driver. And I don't know, let's just do this like 5 times or something. For int I is equal to 0, I is less than 5, I plus plus. What are we going to do each time? We're going to shuffle. Then we're going to print out system.out.println d dot, oh, I'm sorry. Well, no, that should be fine. D dot get percent same, which is a method that returns an int, and we're going to print out that integer. So we're going to shuffle 5 times. Every single time we shuffle, we're going to ask what percent is the shuffled version of the deck the same as the non-shuffled version of the deck. 5, 1, 3, 1. Okay. Now, some interesting things to look at here. Notice in get percent same, this stat, the cards at bucket I, that guy is a card object, correct? This stat, the original cards at bucket I, that guy is a card object. What's the double equal sign? What's that for? It's the primitive equivalence operator. So this is how we measure, this is how we compare primitive types to each other. What's a card? Primitive type or object type? It's an object type, isn't it? Primitive types are byte, short, int, long, char, float, double, boolean. Did I get them all? I think so. Those are our primitive types. So cards aren't one of those, so it must be an object type. So is this incorrect? Seems to be working, doesn't it? I think we talked last time about using the double equal sign for comparing strings, correct? Need to be very careful. In this case, we're using the double equal sign. We are comparing primitive types. We are comparing the pointer values of those cards, not the cards themselves. This is not saying, is the ace of clubs the same card as the ace of clubs? The answer would be yes, in our case, since the ace of clubs only exists once. They are the same card. But if I created a new ace of clubs and another new ace of clubs, and then I said, are these guys equal to each other? The answer would be no. They are not the same object because they'll have different memory addresses. Does that make sense? If I wanted to then compare cards to one another, hint, hint. Okay, this is what I'm about to talk about here is very related to your homework assignment. If I want to compare cards to each other, I am going to have to teach a card how to compare itself to another card. That is, the card will have to say, is my display value the same as his display value, and is my suit the same as his suit? Does that make sense? So there's a difference between saying, are these the same card in appearance versus are they physically the same identical card? Very important we understand that difference when it relates to pointers. So any questions about that? Okay, so now an interesting little experiment we can do here. What if we wanted to write the necessary code? So this is another kind of an advantage of encapsulation. Actually, while I'm thinking about it, let me show you something else here real quick. We have not talked about for each loops in here either, correct? Okay. Nothing difficult about them. They're actually a convenience for us. Let me just do it with the display method and then show you why it would not make sense for show both arrays. So rather than writing a loop that looks like this in our display method, I'm going to write a different loop right below it. The equivalent with the for each. So I'm going to say for card C this loop is functionally equivalent to this loop. This says, for every card named C in the cards, tell C to display itself. That is, this right here literally does exactly that. Spins through every bucket of the cards, sets a variable named C of type card equal to the element at the current bucket, then tells C to display itself. So this is a for each loop. This says for each card C in the cards, do something with that variable. The nice thing with this is it's a very convenient way to spin through things and get objects without having to set them equal to anything or anything like that. The downside is we do not have access to the index. So inside of this for each loop, we don't know if we're at bucket 2 or 3 or 4 or 5. All we know is that we have a card named C, and it's the next card in the list, the next card in the array. Does that make sense? So for each loops aren't necessarily better than for loops. They solve a different problem. They're convenient for iterating over collections of things. If we just care about the individual elements, not the position of those elements. And to show that point, so here, I'll leave this as a for each loop in here. Let's say I wanted to change show both arrays to be a for each loop. Now we have a problem. Because if I would have written this as for card C in this dot the cards, for example, I could have said this dot the original cards. And then I wanted to print this out. Just steal this line. I would print out C. But how do I get the equivalent card in the original cards? I don't have access to I don't have access to the index. Does that make sense? Up here we're saying print the cards at bucket I, but also print the original cards at bucket I. I need to have that index. I want to print out this guy at bucket 0 and this guy at bucket 0. This guy at bucket 1 and this guy at bucket 1. So on and so forth. Okay? So a for each loop would not be a sufficient solution up here because I really need to have access to those individual indexes because I'm doing something with parallel arrays. Does that make sense? So, another little tool for the toolbox, for each loops. And just to show you quickly out here, I'll just say d.display to show you that it still works. So it'll print out some percentages 5 times and then display our. So there's our cards, still displayed fine, right? So you can see it's an equivalent thing. Now, what if I wanted to write some code out here that shuffled the cards 1,000,000 times and kept track of the highest percentage it was the same to the original out of those 1,000,000 shuffles. So I'm going to keep shuffling the cards over and over and over and over and over again. And I want to know at what point, I want to know out of the 1,000,000 shuffles, what was the highest percentage it was the same to the original. How would I write that? What's the worst case that a shuffle could be? None of them match, right? Well, maybe that's the best case for a shuffle. That's completely jumbled. So we're going to create an integer here called winner. We're going to start winner off at 0. All right. So we're going to say cur percent there. Now, rather than printing something out each time, which takes a lot of time, we've seen that before, right? Where I've done a for loop that prints something out each time, it slows way, way down. I'm going to do something 1,000,000 times. We don't want to slow way, way down. So I'm going to say cur percent is equal to get percent same. Then we'll ask the question, if cur percent is greater than winner, then we'll say winner is equal to cur percent. And rather than doing this 5 times, we'll do this 1,000,000 times. So each time through, for 1,000,000 times, I'll shuffle the deck, I'll get the percent the same to the original deck, and then check to see if I have a new winner and set the winner appropriately. After this loop is done, I'll print out winner. It'll print out a single number, which is the highest percent right we had from 1,000,000 shuffles. What do you think it'll be? Think it'll be above 10%? And here I'm going to give us a just so we know what's running in case it takes some time in there in the middle. Because keep in mind, each time through here, it's shuffling those cards by swapping them 1,000 times. So this is doing 1,000 swaps 1,000,000 times. And then asking a question. Actually, just for the sake of argument real quick, let's see how long this takes to do it 100 times rather than starting with 1,000,000. All right, so 9 was the best percentage we had with 100 times. What about 1,000 times? Ooh, 7% for 1,000 times. There's an 11%. 11%. 10,000 times. Ooh, 15. Is that the best we can do? Ooh, 17. Wonder how long it would take before we did 20. Set num times off at 0. We'll say num times plus plus each time through there. So we're going to keep doing this, and actually just to test it first. Let's go to 10. How many times did we need to shuffle before we had 10% the same? And then we'll print out num times concatenated with, let's just do a colon, concatenated with winner. So it'll be the number of times it took, followed by a colon, followed by the winning percentage. And we're going to keep doing this as long as, so this is the difference between a for loop and a while loop. Okay, while loops lend themselves to problems where we don't know how many times it's going to spin. The last example we did with a for loop, we said, we're going to shuffle 10,000 times, and we're going to see what the best we did in 10,000. Now we're going to say, I want to keep shuffling until I finally get 10% correct. See the difference? I knew I was shuffling 10,000 times with the for loop. Who knows how long it's going to take with this? So we'll go ahead and run this. This is going to keep going as long as winner is less than 10. It starts off at 0, so it'll definitely get in there the first time. We'll shuffle, and then we'll do it again if winner is not less than 10. 895 times, we got to 13. What about 15? Oh, big money, big money. 89,544 times, we got to 15%. 16? Big money, big money, big money. This one might take some time. All right, so questions about any of the stuff we've done so far today. So we've built an implementation of cards and decks. I've given you some hints that goes towards your next homework assignment. All right, so what I want to do here is let's take about a 10-minute break. We'll come back, we'll finish Connect 4. Depending on how long Connect 4 takes, we might finish early. We might not. All depends on how complex things get. But out of curiosity, while we're on break, I'll set this to, what do you think the highest number we can set this to is? And have it finish in 10 minutes? Like 20%? Your entire grade rides on this decision. Let's try 20%. Let's just see if sometime across 10 minutes it comes up with an answer for 20%. Interesting? All right, so come back at 8:01, 10 minutes from now. And I'll get this video uploaded, and then we'll finish our Connect 4.